Hey guys, I want to come in and do a presentation on how is food checked for radionuclides. And this comes from Princeton University and is the analysis of foods for radioactivity. Now, there's some important stuff in this, and it's later on, but I will mention that there's interesting information about carriers. This is barium that they have used. If you're interested in the barium, stay tuned. Okay. The analysis of foods for radioactivity should not be considered as a primary defense against human intake. The first indication should always come from information on releases or from measurements of radioactivity in the airborne or waterborne releases. Once the existence of contamination has been established, then the foods can be analyzed to evaluate potential hazard to man. In contrast to most other pollutants, the effects of radiation are considered to have a linear response regardless of the level. Thus, there is no threshold and no absolutely safe limit. Instead, it is necessary to set some lower level below which the radioactivity in foods is no longer of interest as compared with other sources of radiation or other hazards of life. So that's the gauge that they go from. They don't go from a gauge of trying to keep as least as possible. They put it to where the danger is a little bit less than what would naturally happen or from other things, other pollutants. The analytical significance of this is that the lower limits of detection for radioactive substances have been brought down to very low levels, and the simple yes or no testing for acceptability that satisfies regulations for many other pollutants in foods cannot be used. The radionuclides of interest in the case of contaminating events are almost all present now in foods in measurable quantities. Okay? The radionuclides of interest in the case of contaminating events are almost all present now in foods in measurable quantities. Short-lived nuclides are the exception, and the transuranic elements are only present at levels that require considerable effort and analysis. Since most of the radionuclides are already present, measurements made for background information should produce a numerical answer, not merely an indication that the amount is less than some preset value. Okay? The accumulation of background data provides a valuable baseline for evaluating excursions following a contamination event. The natural activity data are equally valuable since the amount of information on food concentrations is presently insufficient for valid comparisons with man-made radioactivity. This report will describe the requirements and considerations for establishing a system to produce acceptably accurate measurements of radionuclides in foodstuffs. The basic concepts will be described, but to maintain the necessary brevity, the detailed procedures that might be used will be given only by reference. During the preparation of this report, FDA has proposed certain recommendations for state and local agencies on accidental radioactive contamination of human food and animal feeds. This material appeared in the Federal Register for December 15, 1978, page 58,790, and is interesting background material for this topic. Okay? That is a source. So take a picture of that, take a picture of that. The most useful classifications of a radionuclide that are those based on the characteristics of the radiation emitted and by the identity of the chemical element. The former is both a guide to a nature of the hazard involved and to the measurement required. The chemical species, e.g. element oxidation state, regulates the metabolic pathways in the biosphere, as well as the nature of any chemical separations required in the measurement procedure. Emitted radiations are generally grouped as alpha, beta, and gamma. Alpha radiation is characteristic of the natural and artificial radionuclides of high atomic weight and consists of energetic particles with very low penetrating power. Its hazard is significant only within the body. It's very important. Within the body, where alpha emitting nuclides can irradiate specific sensitive tissues. Beta radiation appears in both heavy and light natural and man-made radionuclides and consists of electrons possessing kinetic energy and having modest penetrating power. Gamma radiation is pure electromagnetic radiation as it is extremely penetrating. Thus, it can be a hazard externally as well as when it's present in the body. For the present purpose, we are only concerned that the penetrating nature of gamma radiation allows its direct measurement in foodstuffs, while alpha and beta emitters generally must be separated from the bulk constituents of the sample before measurement is possible. Okay, do you understand that to test a food for alpha and beta, which are the actual particles, the alpha is it's the center of the atom. Okay, it's the nucleus, and beta is the electron. Okay, and when they get emitted, it causes ionization of whatever it's closest to. So if it's internal, then it can do some major damage to your cells. Okay, there are other processes in radioactive disintegration that produce emissions. Alpha emission is usually accompanied by low energy gamma rays that may be used for measurements. Okay, alpha emissions is usually accompanied by low energy gamma rays that might be used for measurements. Now that's the issue with it being internal, is that they consider it as a low energy gamma ray, but it's considered low on externally. It's not the same internally when it's right by that cell. When it's that close, you're talking about a different issue at that point, even at low energy. X-rays can be produced by electron capture, and some gamma emitters decay by internal conversion, a process where a fraction of the gamma rays are converted to monoenergetic electrons. These processes do not really modify our measurement concepts, but the decay modes of the significant radionuclides must be known for their accurate measurement. This is so complicated just to understand what's in our food. Okay, the physical half-life of the radionuclide tends to control its persistence in the environment. For example, iodine-131 with a half-life of about 8 days is important for only a few weeks, while cesium-137 with a half-life of about 30 years may be a problem for centuries. For centuries, we should not be allowing any possible more cesium to be released. And it's being done every day from Fukushima and Chernobyl. It didn't just release and stop. This is a continuous thing. A third classification that has some value is the source that produced the radionuclides. Knowledge of the source of radioactive contamination gives a good indication of the nuclides that are to be expected in the sample. This is of considerable assistance in planning the analysis, since requesting a complete analysis for all radionuclides or even for all types of radioactivity in a single sample would lead to a lengthy and expensive operation. Many radionuclides are not potent health hazards, particularly those that are not metabolized by the body. The general groups of nuclides to be expected include the natural activities, specifically radioactive potassium and members of the uranium and thorium series, and the artificial fission products, transuranic elements, and other activation products that result from a nuclear weapon explosion and nuclear reactor operations. Fission products are a very complex mixture at the time of formation, but the short-lived radionuclides die out rapidly, and the mixture becomes simpler within a few days. The transuranics, plutonium, americium, etc., formed by activation of the basic fissionable material, are some interest because of their high toxicity when incorporated into the body, because the strontium deposits in your bone, and the plutonium it goes into soft tissue, all your soft tissue, your liver, all that stuff. Let's see here. Toxicity, let's see. This should be true particularly if the relative hazard of other radioactive contaminants probably present in the same sample is taken into account. Because you don't find the stuff by itself. You don't really find a single radionuclide by itself. It is within a colloid, a group of things that are bonded together. The other activation products are frequently elements that make up steel or other metal containers or structural elements. Radioactive manganese, chromium, cobalt, zinc, and iron are particularly common and result from interactions of the materials with neutrons released in the nuclear reactor or reaction. It is worth pointing out that the contamination of foodstuffs with single nuclides is extremely unlikely. Single nuclides. And that more than one member of any group will probably be present in any sample. The source of radionuclides involved will generally control their distribution in the environment and their consequent transfer to the food chain. The sources considered here will include natural radioactivity, releases from operations of nuclear reactors and processing plants, and fallout from nuclear weapons tests. Natural activity may be of concern when it is enhanced by man's intervention, say by mining to bring materials to the surface and processing the ore to yield other products or waste that may concentrate the radionuclides. Good examples are radium in uranium tailings, in phosphate rock waste, or in slags from phosphorus production. Radium may enter the food chain by dissolving in the groundwater and transferring through plant roots. Nuclear reactors in normal operation release chiefly the radioactive noble gases that are not of interest in considering foods. Reactors do contain large inventories of fission products, transuranics, and other activation products. However, an accidental release can contaminate vegetation by deposition of or through the water pathway. Gaseous releases would most likely involve the volatile elements such as iodine and tritium, or those with volatile precursors such as strontium-90 and cesium-137. Aqueous releases would follow failure of the on-site ion exchange cleanup system, and any water-soluble elements could be involved. Water-soluble elements could be involved. This is the most important part about radiation and radioactivity, is the water-soluble part of it, which is rarely talked about. Processing plants could also have either gaseous or aqueous releases, but only fuel reprocessing is likely to be a significant contributor. In this case, the fission products are aged before processing, and iodine and the gaseous precursor radionuclides are not released. Tritium and carbon-14 are the major airborne products, while the waterborne radionuclides are the same as for reactors. Atmospheric nuclear weapons tests distribute their fission products, transuranics, and other activation products globally, with local deposition being more or less, depending on the size of the weapon and the conditions of firing, high altitude surface or underground. In summary, the deposition of airborne material on vegetation or on soil is the route by which foodstuffs become contaminated, and the subsequent behavior of the radionuclide is controlled by its chemical nature, including solubility in plant or animal metabolism. Contamination of foods can occur either through atmospheric deposition or by transfer with water. In the first case, it is possible for the radioactive material to be in the form of insoluble particulates rather than in a more available form where it will follow the chemistry of the elements involved. A knowledge of the pathway is not absolutely necessary, but it does assist in the deciding on the proper preliminary treatment of the sample of evaluating exposure. For example, surface contamination may have a different significance than the same material present in a plant through the root uptake. Since pathway information is not always available, it is generally considered proper to measure radioactivity in samples that have been prepared as if for eating, so as to approximate the true expected intake. This will usually result in stripping off or washing off of a considerable fraction of the surface contamination. Cooking is generally not part of the preparation, as the mode of cooking and the use of juices, cooking water, and the like cannot be predicted. Milk is often recommended as an indicator food for studying radioactive contamination. It has many advantages. 1. It is available locally at most desired sampling locations. 2. It is marketed rapidly so that short-lived radionuclides such as iodine-131 can be evaluated. It is a major diet component in the United States, both directly and as an ingredient of prepared foods. 4. There is a lot of background information available on previous contaminating events. It is worth noting that some of these advantages are the factors that contribute to the role of milk as a source of human exposure. Milk is a poor indicator of many contaminants. The natural activities, the transuranics, and the activation products have relatively low concentrations in milk. The first two are low because of the poor biological transfer, and the last because their pathways are almost entirely through the aquatic or marine food chain. Thus, the best approach is to know what is in the environment through other monitoring systems, and to design the food analysis program to fit the circumstances. Other monitoring data are also necessary in fixing the geographical extent of the contaminating event. As a general rule, nuclear tests are global in radionuclide distribution, with enhanced levels near the test site. Releases from other nuclear operations tend to be more local in their effects, and the food monitoring plan can be modified to suit. Sampling. The mechanics of obtaining representative food samples will not be considered here since the procedures are common to all types of food analysis. There are certain points that must be considered, however. The first is whether the measurements are being made to determine human intake or the source of the contamination. In the latter case, the early approach used by the FDA for radioactivity is appropriate. I don't agree with that. There, each sample was identified as to its place of origin. For evaluating intake, it is possible to collect total diet samples for a particular population group and to measure the radioactivity in this composite diet. This approach has been described by FDA 2 and by EPA 3 and is normally applied in institutions where mass feeding is carried out. A more elaborate procedure is to simulate a total diet by measuring a number of component food classes selected on the basis of statistical information regarding consumption. This approach was originally used by the Atomic Energy Commission and was applied originally to 3 major cities. This approach does allow identification of specific food types that are contaminated but requires much greater effort and cost in analysis. The use of indicator foods as an intermediate type of monitoring is widespread. As mentioned previously, most of the systems depend on the sampling of the milk, which is available in most parts of the country, either with specific information as to place of origin or the general area of the milk shed. Part of the reason for using milk is the ease in sampling, but it also has significance as a primary food for the youngest and most susceptible population group, which is the children. The younger they are, the worse off it is for them. And it also does tend to pick up several of the fission products, nuclides of the dietary significance, such as radiostrontium, radiocesium, and radioiodine. Most other foods give limited geographical or seasonal coverages and are less satisfactory. The preservation of samples in the field during transport and in the laboratory awaiting analysis is only an aesthetic matter in the case of radionuclides. Decomposition processes do not change the radioactivity, and sample contamination by the radioactivity is unlikely. Thus, freezing, formaldehyde addition, or any other method that will maintain the sample is adequate. Any additive should be checked to assure it does not contain significant amounts of radionuclide sought. For the purpose of this report, we will assume that an adequate quantity of a representative sample is available for analysis, and that another portion is available for storage, either permanently or until the analytical results are accepted as satisfactory. The measurement of radioactivity is a physical process, and it is most efficient when the radioactivity from a relatively large sample can be placed close to the detector. This means that direct measurements of bulk samples are only useful at relatively high levels of contamination, and that most measurements are preceded by preparation. Oh, you're kidding me. Sampling. Yeah. Sorry about that, guys. I'll start this over. The measurement of radioactivity is a physical process that is most efficient when the radioactivity from a relatively large sample can be placed close to the detector. This means that direct measurements of bulk samples are only useful at relatively high levels of contamination, and that most measurements are preceded by preparation and possibly chemical separation to reduce the bulk of the material and to improve the efficiency of the measurement. This is the best we have, guys. I mean, literally the best we have. We shouldn't be doing any more nuclear stuff without first having everything in place to know exactly how to get all this checked, all our food stuff checked. I mean, if you're eating it, it has not been checked. Period. They have to destroy it. And it will go on and it'll tell us how this works. Okay. As mentioned previously, sample preparation may include removal of inedible portions of the food or those portions not generally eaten. For example, citrus rinds, apple cores, outer leaves of leafy vegetables, and above ground portions of the root vegetables would normally be discarded. The general goal is to prepare the food as if for cooking or consumption. Foods generally have a high water content, and a primary method of bulk reduction is drying at room temperature, at elevated temperatures, or freeze drying. Most of the radionuclides of interest are not volatile under those conditions, and losses may be considered only for elements such as tritium or iodine through evaporation. The dried material can be reduced further by ashing at elevated temperatures, by cold ashing with activated oxygen, or by wet ashing with oxidized acids. The sample dry ashing process is most likely to lead to loss of volatile elements, but with care even cesium, polonium, and lead can be retained. So even preparing the stuff, it's difficult to keep what is actually in there in the sample being ready to be measured. Okay, other processes should not lead to loss of elements of interest with the exception of iodine and tritium mentioned above and of carbon. Another approach that is essentially one of reducing bulk is to extract either the original sample or the dried or ashed material with acids or other solvents and thus remove the desired elements from the bulk of the sample. This requires considerable testing beforehand to be certain that the process operates in the desired manner. All these procedures reduce the bulk of the sample and in the case of extraction may also separate the desired constituents from some of the remaining inert material. They do not, however, separate the radionuclides of interest completely from the other radionuclides present in the sample. Such separations will be covered in the next section, but they may not be necessary if the measurement techniques can provide both qualitative and quantitative information. In most cases, this limits the possibilities to gamma spectrometry on the prepared sample. In most cases, this limits the possibility of gamma spectrometry on the prepared sample. If the samples are going to be subjected to chemical analysis, the sample preparation must include the dissolution of the dried or ashed material. This has already been done, of course, in preparation of the wet ashed or extracted solutions. The radionuclides of interest in ashed foods should be soluble in strong acids if ashing temperatures have not been excessive, and this treatment is usually accepted. If there is concern that insoluble particulate may be present, it is necessary to use more drastic methods such as fusion to bring the sample into solution. This should not be necessary, however, if human hazard is the problem under consideration. Okay. At the time of preparation, if not before, the basis of measurement must be established. Depending on the use of data, wet weight, dry weight, ash weight, volume, or even numerical count, e.g. eggs, has to be determined. Frequently, this may have to be done in the field, but fortunately, relatively crude measurements are adequate. Crude measures are adequate. Since unforeseen questions often arise, it is recommended that as many of these quantities be measured as is possible. The requirements for measurements of radionuclide in foods are such that sample preparation is best handled by a group responsible for the rest of the analysis. The chief difference from other types of analytical work is the initial sample. The usual range is from 1 to 20 kilograms, and the reduction of this amount of material is a specialized problem. So when they do sample something, they keep it in between 1 to 20 kilograms of that sample. Radiochemical separations are required to isolate the desired radionuclide both from the remaining bulk constituents and from other radionuclides which would interfere in the measurement. In addition, it is necessary to convert the final product to form a suitable for presentation to the counter. This may involve deposition and precipitation or other processes. There are a number of manuals giving the details of specific radiochemical procedures, and those details will not be repeated here. There are a few generalities, however, that may be of interest. The actual mass of radionuclide that is measured is almost always vanishingly small. This means that many of the normal chemical reactions used in analytical chemistry will not take place. For instance, precipitates will not form. For this reason, it is common to add a few milligrams of carrier material. This is important. Carrier material, which is preferably the inert form of the same element. Where this does not exist, it is frequently possible to use similar elements as carriers, such as the substitution of barium for radium. I read that again. Where this does not exist, it is frequently possible to use similar elements as carrier, such as a substitution of barium for radium. The inert form then follows normal chemistry, carrying the radionuclide with it. Okay? It is also worth noting that even when the separation technique does not depend on the mass of the element present, a carrier may still be useful in preventing unwanted co-precipitation or absorption on glassware. Understand? That is a very important paragraph there. That's probably the most important part of this whole presentation. And I'm not even going to go through this whole thing because we're only on page 5 and it's been a minute. But I showed you where to go. I showed you the keywords to put in there. You can't check food with a Geiger. That is not the proper way to check food. If you're eating it, you can bet it has not been checked. They have to destroy it. They have to turn it to ash, or they have to chemically change it. But I did find this kind of interesting here. They give you the prices of just about everything you would need to have a lab like this. Total cost. Setting up the laboratory would cost on the order of $350,000. Operations should run about $100,000 for salaries, which you need about 6 or 7 people, they said. So that's $500,000. And then $17,500 for supplies, and about $50,000 per year for equipment, maintenance, and replacement. That's a lot of money. Do you think they're really doing that? A lot? I mean, they're not testing our food, guys. Not in the order you think they are. These are the references. General references. So if you're really interested in this stuff, go ahead and check this out. This is a great paper. It doesn't really dive too crazy into it, but it does give you an idea generalistically of how this is done. So price is very important of everything we do. Alright guys, hope you enjoyed this presentation. Please try to finish it, and you'll get an understanding of how this stuff has to be done. And we should not be using more nuclear reactors if this is what it takes. And we get very little in return as far as testing. Tell me what you think down below, and thanks for watching. Bye.